Okay, related rate problems, examples. In a related rate problems, we are given the rate of change with respect to time of one quantity, and we're asked to find the rate of change of a related quantity. We kind of actually did this almost the first day, where you're blowing up a balloon, and so its volume is changing and its radius is changing with respect to time, right? And that's what we're going to look at, or area and time. To do this, we want to find an equation that relates the two quantities. Okay, so we're talking about area and radius. We'll use the area formula. If we're talking about volume and radius, we'll use the volume for that particular thing, which hopefully has a radius in there. We're going to use the chain rule and implicit differentiation to differentiate both sides with respect to time. Okay. Procedure: identify the rates you know and the rate to be determined. Write an equation that relates all the variables. You may have to do extra work to express the equation in one variable. So oftentimes you'll be drawing a diagram to kind of help you out in this. So there's ones we won't be, and there's ones we will be. Take the derivative of both sides with respect to time. Remember to use the chain rule. Substitute all known values and rates and solve for the unknown rate. Again, you may have to do some extra work to determine a value. And we'll see that as we go through this. Oh, and my smartboard, oops, is off. So let me drag this down.
Which caliber?
I know, I just did.
You get to do it again.
Yeah. Like, where I draw is fine, right? The drawing appears where it's supposed to, but if I go and click down here, it's like clicking whatever. I know. You can live without it, but yeah, just do not. Anyway, so if area is equal to pi r squared, so there's actually a relation where we've given you that, then determine expression for dA by dt in terms of r and dr by dt. Okay, so basically what we're going to do is we're going to differentiate both sides of the equation. A equals pi r squared, right? Let's write that out. A equals pi r squared, and we're going to differentiate with respect to time. So on the left, we're going to end up with dA by dt, and on the right, we're going to get dA by dr, right? We'll be taking the derivative of area with respect to times dr by dt, right? Because we're taking the derivative of the right-hand side with respect to time, which is going to be dA by dr and dr by dt. All right, so dA by dt is just that. dA by dr is 2 pi r times dr by dt. And that's it, done, right? We're going to come back to this in like example 4 and go a little bit further with it. That one was okay. All right, moving on. We're not. I can't, if I hit over here, I'll be, damn it. Yeah, it's probably, the microphone is sensitive and pick that up. It's okay. If y is equal to 4x squared minus 3x plus 5, then determine an expression for dy by dt in terms of x and dx by dt. So again, we're going to take the derivative of both sides with respect to time, and so the left side will be dy by dt, and this will be dy by dx times dx by dt. Okay, so actually working this out, we get dy by dt is equal to, so dy by dx, just this derivative, right? It's just going to be like 8x minus 3. And let's enclose that in parentheses because using the chain rule then, of course, we have to write dx by dt. And we're done. And if you're thinking it can't be that, you're right. Okay. These are just kind of the beginner examples, just to sort of show you, hey, if you have this, and then, all right, hang on. The only way to change pages is this way. If volume is pi r squared h, then determine expression for dv by dt in terms of rh dr by dt and dh by dt, right? Because now, when we take the derivative with respect to time of the right-hand side, we have two variables there, right? Now, we're going to want to avoid that. having two variables, and I'll show you in a further example how we can avoid doing what we're about to do here. All right, so what are we going to do? We take the derivative with respect to time, so dv by dt is equal to, so now we have basically product, right? So we've got pi r squared, pi is just a constant, right? But pi r squared times dh by dt, right? I mean, the derivative with respect to h is 1, and then times dh by dt, plus h times the derivative with respect to time of pi r squared. So I guess I could legitimately have just written pi h, right? But doesn't matter. So we have pi r, well, we have dv by dt is equal to pi r squared dh by dt plus, and the derivative here is going to be 2 pi r, so we've got h times 2 pi r times dr by dt, right? Again, we're taking the derivative with respect to time of this, gives us 2 pi r dr by dt, and sort of cleaning it up a little bit. dv by dt is pi r squared dh by dt plus 2 pi rh dr by dt. So we're in terms of RH, dr by dt, and dh by dt. Okay, so RH, dr by dt, dh by dt. And again, usually when we solve this kind of problem, we want to get it into one variable, right? So we either want to solve for h in terms of r, or solve for r in terms of h, so that we're only working in r or h, depending on what we want to find, right? If I want the rate at which the height is changing with respect to time, then I'm going to want to solve for r in terms of h. So all I have is one variable h, and if I want the rate of the radius is changing with respect to time, then I want to solve for h in terms of r and replace it so I have an equation which either has an r in it or an h, but not both.
How come the dr by dt comes in the second line of the equation?
So what we're doing is we're saying we're taking the derivative of this. So I could have just gone straight to like h times 2 pi r dr by dt. So I kind of split out just to say, you know what, hey, we're taking the derivative with respect to time of this, and it's a product, right? So maybe the pi should be out there. I don't know, pi h, because those are constant with respect to r. I can't touch there. I tried. It wouldn't. Okay. The for real stuff. So this goes back to example 1, but it's more a real example, right? A pebble is dropped into a pond, causing ripples in the form of concentric circles that are growing in size. The radius of one circle is growing at a rate of 0.3 meters per second, right? So if you think drop of water and it's propagating outwards. Determine the rate of change of the area when the radius of the circle is 2 meters, okay? So the first thing we would do is we need a formula to relate A and R, right? Related rates. So we need a formula to relate A and R. Okay, so the area of a circle is pi r squared, right? It's a formula to relate A and R. We take the derivative of both sides with respect to time, which we've already kind of done, right? Well, kind of, not kind of done, but we have done, but let's redo. So dA by dt is, let's go a little bit formal here, dA by dr times dr by dt, which is 2 pi r times dr by dt. Now, we want the rate of change of area, which is fine. We know the circle is growing, so that 0.3 meters per second, that's dr by dt, right? The radius is changing at a rate. That's dr by dt is 0.3 meters per second. And we want when the radius is 2 meters, okay? So we go into this, right? We've got dA by dt is 2 pi my radius is 2, right? That's what we wanted to figure out. What is the rate of change of area when, right, at the instant when the radius is 2 meters, if it's changing radius at a rate of 0.3 meters per second, right? So r is 2, dr by dt, right? Change of radius with respect to time. So they did give us that rate. And so we get what? 2 times 2 is 4 pi, 4 times 0.3 is 1.2 pi meters per second. Oh wait, area, meters squared. So it's changing at the area is changing at a rate of 1.2 pi meters squared per second. Okay, so that's our first full related rate. Okay, so now we're going to do, oh wait, 5, 6, 7, 8, 7 more examples. You might as well see lots, right? So that at least when you're doing ones of these, you say, okay, I've seen something like that, I know how to kind of handle this. Air is pumped into a spherical balloon. If the volume of the balloon is increasing at a rate of 20 cubic centimeters per second, okay, so volume is increasing at a rate of 20 cubic centimeters per second, the rate of change of volume with respect to time. Then how fast is the radius increasing when the radius is 30 centimeters, right? And in this case, what we're really saying is, hey, it's pretty easy for us to figure out the volume of a balloon, but it's not so easy to measure the radius. So if we, know the rate at which the volume is changing, then we can figure out the rate at which the radius is changing. All right, so you need to relate. We need a formula that relates volume to radius for a sphere, and that formula is V is equal to 4/3 pi r cubed. Okay, so that's just straight off of a formula sheet or out of your head or whatever, which if it comes from there, hopefully is correct. We're going to differentiate both sides with respect to time. Okay, we only have one variable, right? I mean, well, two, v and r. So dv by dt is equal to 3 times 4/3. That's going to be 4 pi r squared times dr by dt. So we look at that and we said, what are we trying to find? We know dv by dt. We're trying to find the rate at which the radius is changing, right? So it says, then how fast is the radius increasing? So they're asking us for dr by dt. So let's rearrange this so that it says dr by dt equals. Now we'll do that by dividing both sides by 4. You don't want to do that. You want to go dr by dt is equal to 1 over 4 pi r squared times dv by dt. Okay, so instead of dividing both sides, which gives you this awkward dv by dt over something, that's kind of silly, right? So just write it as 1 over 4 pi r squared times dv by dt. That's a general thing, right? So that's always going to work. And now we substitute in the information we have, right, which is the rate at which the volume is increasing. So this is going to become 20 when the radius is 30. That's going to become 30, and we're just going to work it out. So let's keep things on one line or one page. So it's 1 over 4 pi times 30 squared times 20. If I wanted to go a little bit more general, then I could have multiplied by the 20 and got this as like, 5 over pi r squared. So I could have written, well, here, let's do that. Let's leave this. So just say r squared here. So that's 5 over pi r squared. Okay. Now, we don't need to do that in this case, but we might do that if we had to figure out a number of different dr by dt's, right? When the radius is 30, when the radius is 50, when the radius is 100. If we had to do that, having this as a little more general formula, right, just a little more simplified formula, would make things a little bit easier, but we didn't need to do this. So 4 pi 30 squared 30 squared is what, 900, 5 goes into 900, 180 times. So it's 1 over 180 pi. We need units, it's radius, okay, and it's centimeters, so it's going to be centimeters per second. So 1 over 180 pi centimeters per second. Okay. That's exact. We could give some decimal equivalent. If you needed to, you could change it, but you can't because you don't have a calculator. But, if you had a calculator available to you, you could change this. Yeah, look at that. We're 5/11ths of the way through. Maybe this isn't so bad today. Move through it a pretty... Yeah, but we're only doing 11 because the other 3 are trig. So we're going to hold off for a couple of days. So rest of today, work period, all of tomorrow, work period, whatever the day after tomorrow is, like call it Wednesday, would be trig, and then Thursday max min, and then you're off for a little while. Length of a rectangle is increasing at a rate of 3 centimeters per second, and the width of the rectangle is increasing at a rate of 2 centimeters per second. How fast is the area of the rectangle growing when its length is 15 and its width is 8? All right, so let's come up with an expression for the area of a rectangle, which is what? So area is length times width, right? We are going to take the derivative of this with respect to time, both sides, right? So dA by dt. Now this is a product, right? L times W, so it's going to be L times the derivative of W with respect to time, which is 1 times dW by dt, right? Or just dW by dt. Plus, okay, now it's the W's turn to be here, times the derivative of L with respect to time, which is dL by dt. So it's just a product, right? L times W, we're just using the product rule. We know the length of the rectangle, so that's dL by dt. And the width of the rectangle, that's dW by dt. And that's L. And that's W. So we got everything we need, right? In order to figure out the rate at which the area is changing. We got a length, we got a width, we got the rate of change of increase of width, the rate of change of increase of length. So we just plug in the numbers. dA by dt. So when the length is 15, the width is changing at a rate of 3, and the width is 8. Now let's bracket this. And the length is changing at a rate of 2. Wait, sorry, the length is changing. That's a 2 there. That's a 2. That's a 3. Yeah, length is changing at a rate of 3, so we got 30 plus 24. So area at that moment is changing by a rate of 54 square centimeters per second. Okay. Questions, comments, concerns? Okay, now we get into the more exciting ones. A water tank is in the shape of an inverted right circular cone, right? Just think of an ice cream cone. That's an inverted right circular cone. With a depth of 5 meters and a top diameter of 4 meters, water leaks out of the tank at a rate of 1/12 of a cubic meter per minute. How fast is the water level in the tank dropping when the water in the tank is 4 meters deep? So, let's kind of draw the cone. And we know that this cone is 5 meters tall. We know that this cone has a radius of 2 meters. Remember, if we're doing a formula for a cone, it's not in terms of diameter, it's in terms of radius, right? So let's convert that diameter into a radius of 2 meters. height of 5 meters. There's water leaking out, right? So 1/12 of a cubic meter per minute. So let's throw a negative in there, right? Because the volume is decreasing, right? So the volume of the cone is decreasing by, so 1/12 of a cubic meter. So negative 1/12 cubic meter per minute, right? That's what's going to happen there. And if we want to generalize this, and we say we got R and we got H. So what's going to, imagine the water level is here, right? So when the water level, it starts out, let's say it started out full and it starts leaking out. Well, the radius changes and the height changes, but these guys are similar triangles, right? So I've got a triangle that's got a radius of 2 with a height of 5, and I got a triangle with a radius of R and a height of H. Right? Those will be similar triangles, which means we can set it up as a proportion. Okay, so let's see, what have we got here? We are given, so let's just kind of try and list the information we have. We know the rate of change of volume with respect to time is negative 1/12 cubic meter per minute. Okay? So we've got dV by dt. We are asked to find dH. How fast is the water level in the tank dropping? So the water level will be the height, right? How high is the water in the tank? That's the level. So we are given this. We are asked to find dH by dt. Okay? We don't care what rate the radius is changing. We're asked to figure out what the height is changing. Okay? When h is 4 meters. It's a related rate. We need an equation that relates V and H, right? So the equation relating V and H, so V and H are related by V is 1/3 pi R squared H. Okay, so you either know that or you look it up. That's the volume of a right circular cone, right? It's like 1/3 the volume of a cylinder of the same size. This would be easier if we can express this solely in terms of H, right? Because then we just do the derivative of both sides. We'll get a dH by dt. We won't have a dr by dt in there, which we don't know. And, okay, so this will be easier. If we could express V as a function of H alone. All right, so let's scroll this, about there. Now, can we do that? Yeah, we have a relationship, right? The relationship we have is that we know that from the diagram, in similar triangles, we know that R over H is in the same ratio as 2/5. Because those are similar triangles. They're both 90 degrees at the top. They both have the same angle at the bottom there, that whatever angle is down here, right? Okay, so we got these similar triangles, and we want to get H. So what do we get? 2H is 5R. So H is actually, sorry, we don't want H, we want R, right? So we want to get rid of the R, is 2H/5. So where I see R in the original formula, I can replace it with 2H/5. And now the right-hand side will be 1/3 pi, and then we'll just have H's, right? Then we'll take the derivative with respect to t of both sides, and we can solve the problem. Okay, so what do we got? V is equal to 1/3 pi R squared H. Okay, but it's not. We're not writing R. We're writing 2H/5. Okay. If we were looking for the rate of change of radius with respect to time, we would have solved this for h and substituted in, so we had an expression only in terms of r. So what does that give us? Let's just sort of simplify. So 2h squared is going to be 4h squared over 25. So we're going to get a 4 pi h cubed over 75. Right? That's going to be your formula for volume. 4 pi h cubed over, and all I did was square the 2h over 5, giving me 4h squared, and that's up top, times a 1, times a pi, times an h, 4 pi h cubed, and on the bottom, 3 times 25 is 75. All right, shifting down. Move this over here. Okay, so dv by dt is going to be dv by dh times dh by dt. So I'm going to go across to avoid. Which is going to be, do this, right? So it's going to be 3 times, which the 3 goes into the 75, 20 times. So we're going to get 4 pi h squared over 25, right? Multiplied by 3, the 3 goes into the 75, gives that as 25, right? Times dh by dt. Now, we want dh by dt, right? That's what we're trying to find, is the rate at which the height is changing with respect to time. So dh by dt is going to be, so I'm going to multiply both sides. Remember this goes there, right? I'm going to multiply both sides by the reciprocal, so it's going to be 25 over 4 pi h squared times dv by dt, and we know h, right, 4, and we know dv by dt, negative 1/12. So all we have to do is substitute in and extend the page to get the substitution. So 1 sec, that's the line. Okay. So that's equal to 25 over 4 pi 4 squared times negative 1/12. Right? So dh by dt will be negative, which is what we expect, right? The height's going down. We're not pouring water in. Water is leaking out or is being released. So dh by dt should be negative. All right, what do we got? We got a 25 negative. We got 4, 4, 12 is like 2s and 3s. There's nothing that's going to cancel into that 25. So what do we have? A negative 25. 4 times 4 times 4 is 64. Times 12 is 640 and 128. 768. 768 pi. Yes. Well, we'll either give you easier numbers or, you know. And if we actually let you have short access to a calculator, it'd be negative 0.01 meters per minute. Right? So the rate of change of height, when it is 4 meters tall, it's going down by 0.01 meters per minute, or 1 centimeter per minute. Okay, so not a huge rate of change of height. Yeah.
How do you know if you used the 5 or the 4 for the height? Like I know earlier when you figured out R, you used the depth.
So initially they told us the cone itself, right, the actual physical object that's holding it, has a height of 5 meters, okay, and it has a diameter of 4 meters. So the initial drawing was this, right? Here's the initial cone. Now the R and the H that I drew in here is just in a general situation, right? So forget that I know the height at which I want it, or even the rate at which it's going down, right? I'm just going to say, look, I got a cone that has this dimensions, And the r and the h are going to be changing, but they're always proportional to this, right? This r is to 2 as h is to 5, right? Or r over h is always equal to 2 over 5. Okay? So that's regardless, right? Like, forget anything else about the problem. This is sort of the first thing you draw. If I then wanted dr by dt, then you would try and get this expressed simply in terms of r. So we would have to write this, so we solve for h in terms of r. So down here we'd be looking at h equals 5r over 2. We would substitute that in. So we had an expression only in terms of r. Then we take the derivative with respect to both sides. We have dv by dt and dr by dt. Then we substitute in these things. When the tank, how fast is the water dropping when it's 4 meters deep? That's what we're going to substitute right at the very end, right? So this rate is constant, and if we wanted to know what level is it dropping when it's 1 meter deep, we'd put a 1 in, 2 meters, 2, and so on. Okay, so we're just kind of looking at a more generalized thing here, just to sort of say what's going on in this situation. Okay, and how are we going to relate these two things? What's next? A 2-meter tall statue is being moved at a rate of 0.4 meters per second away from a lamppost with a light that is 5 meters above the ground. At what rate is the tip of the shadow of the statue moving away from the base of the light post? So if you can just sort of imagine, you got this statue and there's a light and it's dark out, I guess, right? And there's a light post that's 5 meters high and you're pushing the statue. You know that its shadow is going to change, right? And so at what rate is the shadow, and then B, at what rate is the length of the shadow of the statue change? It's going to require two different things, right? So two different solutions. We're going to have two different diagrams here, right, when we go to work this out. Okay, so let's try the first one. What was I reading? Something about like producing vitamin D from sunlight, and it said if your shadow is longer than your height, then you're not actually producing vitamin D, right? The angle of the sun isn't high enough for the UVB rays to make it through the atmosphere. So the sun has to be reasonably high, which doesn't happen that much here, right? So if your shadow is longer than your height, then the sun is at a lower angle, and you're just not getting the UVB rays you need to produce vitamin D. If your shadow is shorter, then it's high up, and you are producing. So you can use that as a rule of thumb. In the meantime, you should be supplementing or not. Read up on the stuff yourself. Figure it out. Okay, A. So let's draw a picture. So there's the light post, which is 5 meters high. Here's the statue, which is 2 meters high. You can see we've got similar triangles going on here, right? This is the distance. Let's call that distance x. Let's call this distance here a, which makes this distance here x minus a. Okay, so we've got three distances here. We are changing a, right? A is what's changing in a, okay? Because we are moving we're moving the statue away. So in this particular case, the rate of change of the distance of the statue from the light post is 0.4. Okay, so that's dA by dt. We are trying to figure out the rate at which the tip of the shadow, here's the tip of the shadow, right? So we're trying to figure out, well, how is x changing? Okay, how is this distance changing? So dx by dt is what we want to find. So using the diagram in similar triangles, using diagram. So drawing a diagram can help in coming up with the relation, right? So you might want to draw a diagram. Using diagram and similar triangles. That's a triangle. We know that x over 5 is equal to x minus a over 2. Okay, so the base is to the height. Base is to height as base is to height. similar triangles. We want to solve this for x, right, in terms of a. So what do we got? 2x is equal to 5x minus 5a. Negative 3x is equal to negative 5a. And x is going to be 5/3 a. Now, sliding this down manually because I can't. Oh, I guess when I do this, it's also manual. I just can't touch there. All right, what do we got? We want dx by dt, and that's going to be equal to dx by dA times dA by dt. So dx by dt is equal to, so dx by dA, the rate of change of x with respect to a is 5/3 times dA by dt. All right, and what did we want to find? We wanted to find dx by dt, and what did we know? We knew dA by dt, so we're just going to substitute in here and say the rate of change of the distance, the tip of the shadow. And you will get 2/3 of a meter per second. So that's A. B is going to require a separate diagram. I'm going to need to insert a page here. Insert blank page. Okay, so in 8B, what do we want to know? What do we want to know? At what rate is the length of the shadow of the statue changing? Okay, so again, let's draw this out. We know this is 5. We know this is 2. In this case, we're going to call the distance from the light post to the statue, we're going to call A. We know at what rate that's changing, right? We know that the statue is moving away from the light post at 0.4 meters per second. And what we want to know is, so at what rate is the length B changing, right? Because B is the length of the shadow. Okay, so the way I've drawn that, we're not using the x minus a. We're saying this length is B. At what rate is B changing? Okay, again, from similar triangles, B over 2 is equal to A plus B over 5. Right? So the length of the shadow to the height of the statue is equal to the total length to the total height. Solving that, we get 5b is equal to 2a plus 2b. 3b is equal to 2a, and so b is 2/3 a. Okay, we want to work out dB by dt. dB by dt is going to be the rate of change of b with respect to a times the rate of change of a with respect to t. Okay, so we have this expression for b, right? So we can take its derivative. dB by dA is just 2/3. So the rate of change of b with respect to time is 2/3 times dA by dt. And we know dA by dt, right, 0.4. So dB by dt is 2/3. So that's 0.8 thirds, which we would never do, which is 8 over 30, which we would do, which is 4 over 15, and that is in meters per second. Okay, 8 down, 3 to go. That bad? A dentist appointment. Even that is preferable to calculus. I'd rather go to the dentist than sit through this. And the funny thing is, they're going to scrape some stuff off his teeth, and do you know what that stuff is called? It's called calculus. I kid you not, look it up. He's going to sit in the dentist chair and get the calculus scraped off. A hot air balloon is 60 meters directly above SAM and maintains its altitude, so it's going to stay at an altitude of 60 meters, even when the wind is blowing it horizontally at 5 meters per minute. At what rate is the distance from the balloon to SAM increasing when its horizontal distance from SAM is 20 meters? Right? So think about the distance from SAM to the balloon. It starts out at 60, and then as it starts moving, it's now the hypotenuse of a triangle, right? And that's changing at a rate, and we want to know what is the rate at which it's changing at this particular moment in time. So let's draw a picture. So there's the balloon, and there's SAM. And the balloon is going to move this way at 5 meters per second. And at some point, we're going to have this situation, right? So this will be 60. We'll call this distance x. And I was going to call this d for the distance, but we'll call it z. Because if I use d, then we get dd by dt, right? And it's better to have dz by dt. I think it's less confusing. So this 5 meters per second is dx by dt, right? It's the rate of change of the horizontal. So horizontally, the distance is changing. The horizontal distance, which is x, is changing at a rate of 5 meters per second. We need to relate z and x. So how do we relate z and x? Pythagorean theorem, okay, yeah. So relate. It's all about related rates, right? So we need a relationship between z and x, which is the Pythagorean theorem. So z squared is equal to x squared plus 60 squared. We want the rate of change of z, right? That's what we want to find. How is z changing? Because z is the distance from Sam. If they had a rope that they had given to Sam and said, well, how much rope? You know, here there'll be 60 meters of rope, and then that length of rope would increase as, you know, so if they were a slightly tethered balloon or something, but blowing along still, you know. Or if that were a kite, which was flying straight overhead, I don't know what kind of wind you'd get. Pretty good updraft. And it started drifting sideways. Maintaining its, okay, so taking the derivative with respect to time of both sides, we get 2z times dz by dt is equal to 2x times dx by dt. So the derivative here with respect to time, plus that's a constant, so the derivative is 0, right? 60 squared root of 0. So, what do we want? Well, we want dz by dt. How are we going to get that? We're going to divide both sides by 2z. That gives me 2x over 2z, which is just x over z times dx by dt. All right, now if for some reason we happen to know x and z and dx by dt, then life would be good, and we do actually know all of those. Oh, no, we don't quite, do we? What do we know? We know dx by dt, and we know x, but we don't know z. But we can figure out z, right? We know that x is 20, so here, let's go over here. Say when x is equal to 20, then z is the square root of 20 squared plus 60 squared, right? Because we need a z down here, right? We know x, we know this, we know this. We don't know this, but we can figure it out, right? When x is 20, we can figure out z, so let's do that. So, all right, what do we got? 400 plus 3600? which is 4,000, which is 20 root 10, right? It's 400 times 100. Or sorry, it's 400 times 10, and the root of 400 is 20, right? So it's 20 root 10. Okay. Now, we can move down and replace, put everything in that we know. Okay, so dz by dt, the thing we want to find, is equal to 20 over 20 root 10 times 5. Okay, so they told us that x was 20, right? They said when the horizontal distance is 20 meters. Using that, we calculated what z was, right? So we knew what z was, and the rate at which z is changing, and we know the rate at which x is changing, it's being blown by a 5 meter per second wind, right? So we get 5 over root 10, which is 5 root 10 over 10, which is root 10 over 2. Okay, so dz by dt, let's just go over here. dz by dt is root 10 over 2 meters per second. Okay, which is about minute, right? It's 5 meters per minute. Minute? Where's the question? Yeah, 5 meters per minute. Okay, sorry. So it's meters per minute, which is about equal to, if you actually plug that into a calculator, you get about 1.58 meters per minute. So if you did start with a rope that was tethered to the balloon, and then the balloon started moving, you'd be laying out rope at the rate of 1.5. When the balloon was 20 meters horizontally away, the rope would be spooling out at 1.58 meters per minute.
That's super slow.
Yeah. It's a hot air balloon. How fast do they go? They're limited. Look, if it's really windy out there, they don't fly those things, right? That's when they get smacked into buildings or something. We can't go up fast enough. All right, what do we got? 2 more? 10. Oh, okay. Well, easy. Not really. Okay, so we have x cubed minus 3xy equals 12. We have dx by dt. We want to get dy by dt when x is equal to 3. Okay. So we're going to start off by taking, so let's start with, we got x cubed minus 3xy is equal to 12. We're going to take the derivative with respect to t of both sides of this, right? So that's going to be 3x squared times dx by dt. Minus 3, and then let's throw in a set of square brackets. So now we've got this xy, right? We're doing the derivative with respect to t of x times y. It's a product, right? So it's going to be x times dy by dt plus y times dx by dt. Sorry, yeah. Plus y times dx by dt. And the derivative of 12 with respect to time, well, that's constant, so it's just 0. All right, so, I mean, in theory, we could just throw the stuff in right now, right? But we're not going to. I don't know. Because that should say dx by dt, by the way, right? I know, you're about to point that out. So let's, so what we're going to do is we're going to actually go through, we're going to solve this for dy by dt, right? You say, well, you know, do we have to? Yeah, okay, yes. And the reason is, if you're going to use this, right? I mean, if you're doing anything useful, then probably you're going to use this multiple times, in which case it's better to have a simplified expression for dy by dt. if you're programming your computer to do that or something. I mean, here it's a pretty trivial calculation, but imagine you've got something that's really complex, then the simpler you can get it, the faster the computer can run through. Okay, so efficiency sometimes does matter, and it depends on what kind of device you have and your processing power that's available and all that good stuff. All right, so what do we got? Let's go 3x squared. Well, actually, let's do a couple of things. Let's divide through by 3, right? So the 3's are gone. So let's go x squared times dx by dt minus 3y dx by dt is equal to x dy by dt. So, whoops.
Yeah,
You're about to point that out, right? I know.
of course.
I thought I'd leave it there. See if. Okay, so what do? We divide it through by 3 and we move this expression over to isolate dy by dt, right? So now I'm going to really isolate dy by dt. So dy by dt, you divide both sides by x, and the simplest way of doing that is to just multiply by 1 over x. So it's going to be 1 over x times this side here, right, which is x squared dx by dt minus y dx by dt. And at this point, I don't think we need to go any further with the simplifying. We sort of could, right? We could multiply through and get an x and dx minus y over x. But at this point, we're pretty good. It's not too bad. So we can substitute in what we know, right? And so what do we know? Well, we know dx by dt, right? And we know x. We don't know y. So we got to get y. How can we get y? Oh, well, we got this formula up here, right? X squared. So here, let's go over here. When x is equal to, what did they say x is equal to? 3? So when x is equal to 3, we get 3 squared minus 3 times 3y is equal to 12. So when x is 3, we need y, right?
3 cubed?
Yeah.
3 cubed. That's what I wrote, 3 cubed. Change that. It's almost imperceptible. All right, what do we got? We got 27 minus 9y is equal to 12. Negative 9y is negative 15. Y is 15 over 9, which is 5/3. Okay, now let's go down and substitute in. So it's just kind of like the last one, right? Where we had to actually figure out, hey, what is this value when, like, I don't have that value? Okay, so we knew x. We knew dx by dt. We didn't know y. We had to go back to the original equation, get y. We've done that. So now dy by dt, which is what we were looking for, is 1/3. And we got 3 squared times 6 minus 5/3 times 6. So I can write that as 6 over 1. And what's that? So that's going to be a 2 minus 10. We got 9 times 6 is 54 minus 10. dy by dt is 1/3. And we got 54 minus 10. So 44 over 3. And let's just let's make that explicit, right? I'd written one more line at the bottom, but it's painful to scroll down. Okay, so dy by dt is, there are no units with this, right? So that's it. Okay, speaking of that's it, one more. One more. Gotta be done shortly after 3. That's kind of. At 1 p.m. At 1 p.m., boat A is 25 kilometers due north of boat B. If boat A is sailing west at a rate of 16 kilometers per hour, and boat B is sailing south at 20 kilometers per hour, determine the rate at which the distance between the two ships is changing at 1:30 p.m. Okay? So all of these related rates, there is no constant rate of change, right? The rate of change depends on what's going on, right? Because they're moving away from each other. Okay, so we got boat A, we got boat B. They are 25 kilometers. Boat A is moving this way. Let's call that little A, and that's 16 kilometers per hour. And B is moving at 25 kilometers per hour. And we'll call the distance between them Z again, right? Okay, so based on what I've written, the rate of change of A is 16 kilometers per hour. The rate of change of B is 25 kilometers per hour.
Boat B going 20 kilometers.
Right. 20. Look at my notes. It even says 20. That's good. I let you finally catch one before I did. And yeah, that was really nice of you. Here's the relationship between ZA and B, right? Z squared, which is the hypotenuse of this particular right angle triangle, which is A squared plus B plus 25, right? Because it starts here, so there's that initial 25, which is then increasing by B. Okay, so we've got that. We're going to take the derivative of both sides with respect to time. So the derivative of the left side is 2z times dz by dt. That's what we want, right? We want dz by dt. That's the distance between the two boats. We want to know the rate at which that's changing. So we got 2a times dA by dt, which we know, right? dA by dt. Plus, derivative of this is 2 times b plus 25 times dB by dt. And you don't worry about the rest of it, right? Because it's just a b, which is a 1, and then a constant, which is 0. So there's the derivative with respect to time of both sides. We want, okay, now wait a sec, what do we need? At 1:30 p.m., right? What do we have? We don't know Z yet. We need to figure out what Z is. We don't know what A is. We don't know what B is. Well, we kind of know. But we do know this and this. So what we need to know is at 1:30. So at 1:30, or 13:30, we know that A, that's half an hour, right? So how far did it go? What's this distance at 1:30? 8. What's this distance? 10. So we've got 8 and we've got 35, right? Or 25 plus 10. So at 1:30, A is equal to 8 and B is equal to 10. Right, it's good, right? So we got an A, we got a B, we can put those in. We know dA by dt, we know dB by dt. All we need is Z. Well, Z is the square root of, so Z is equal to the square root of 8 squared plus 10 plus 25 squared. Right? It's not a squared plus b squared, it's a squared plus 25 plus b squared. So Z is equal to, and I'm just going to give you the simplified version, I believe that's 1,289. Okay? Yeah, because 8 squared is 64, 35 squared is 1225, right? And our square number is ending in 5. Write down 25, then take the first digit, multiply it by the next higher digit. So 35 squared, 3 times 4 is 12, 25. 55 squared, 5 times 6 is 30, 25. 75 squared, 7 times 8 is 56, 25. You don't believe me? Try it for yourself. Okay, so that's 1225 plus 64. You need this, right? Especially in a class like, thank you.
Like 35 squared, 45 squared.
All right, so look, everything's divisible by 2, right? So dz by dt is 1 over z times a times dA by dt plus b plus 25 times dB by dt Okay, so slide that down, plug it in, and we'll be done.
I was,
Okay, so that's 1 over the square root of 1289 times A, which is 8, times dA by dt, which is 16, plus 10 plus 25, times dB by dt, which is 20. So dz by dt, so the 2's divided out because there were 2's everywhere, right? So 2, 2, 2, cross off 2. And that is about 23.06 kilometers per hour. Okay, so now that you guys are back, we're done. It was easy.